Hello everyone, welcome to today's session on normal probability distribution. Before moving to the normal probability distribution, let us study some prerequisite basic definitions for the normal distribution. The first one is random variable, a function that assigns a real number to every outcome of a random experiment is called a random variable. Basically, the normal distribution is studied on the considered random experiment which has some specific outcomes. To all those outcomes, we assign with a real number a function that assigns such real numbers, we call it as a random variable. The second one is continuous random variable. The definition says a random variable that takes infinite number of values for assigning outcome of random experiment. So we know that the definition of the random variables, a function that assigns a real number. If this function takes infinite number of values in order to assign the outcomes of experiment, then we call this particular random variable to be as continuous random variable. Moving to next definition, the probability density function. The definition says like, for every x belonging to a continuous random variable, we assign a real value f of x satisfying the condition f of x is greater than or equal to 0 for all random variable x, and integral minus infinity to plus infinity f of x into dx is equal to 1. It means we have the experiment. To that experiment, we have the outcomes. To each outcomes, we assigned a random value x, and to each random value x, we are assigning one more value called f of x, and this f of x gives the probability of getting the random variable x, or in other words, this f of x gives the probability of happening of the event x or happening of the outcome x here. So moving to the next, normal distribution. Let x be continuous random variable for any mu, sigma square. The probability density function of normal distribution is given by f of x equal to 1 by sigma root 2 pi into e to the power of minus of x minus mu whole square divided by 2 times the sigma square, where f of x is greater than or equal to 0 for all x, and integral minus infinity to plus infinity f of x into dx is equal to 1. It means we have the experiment. To that experiment, we have the outcome. To each outcome, we have assigned a random variable x, and the probability distribution of the outcome is given by the value f of x, which takes this particular standard form. It means that if in any random experiment, if the probability distribution of the outcome follows this particular probability density function, then we call such distribution to be as a normal probability distribution. And here the mu stands for mean of normal distribution, and sigma stands for the standard deviation of the normal distribution. And the x is called the normal variate. X is a random variable assigned to the outcome, and here x represents the normal variate. Now, so we study some standard results on the graph of the function f of x. Here we can see, so this is the probability distribution function or probability density function, we call this as. If we plot a graph for this function f of x, so we can observe the nature of the graph in this form. So this is a normal probability curve. This is a curve of f of x, and this is the line x is equal to mu. So there are some special characteristics to this normal probability curve. The first one is the graph of probability density function of normal distribution f of x is a bell-shaped curve. So we can observe the graph here. If we plot a graph, that gives a bell-shaped curve. And the second one, the graph of f of x is symmetric about line x is equal to mu and is called normal probability curve. So we can see the line x is equal to mu here. This line is dividing the complete curve into two equal halves, right? This is a normal probability curve. That curve is divided by the line x is equal to mu, and the region in the first quadrant is symmetric about the region in the second quadrant here. Next, the line x is equal to mu divides the normal probability curve into two equal parts with area 0.5 square unit. We know that the maximum probability value can be equal to 1, and this curve, the area below this curve, if we consider, the value will be equal to 1. The complete area below the normal probability curve will be equal to 1 because the maximum probability value can be only 1. Now, since this graph is symmetric about the line x is equal to mu, the area below the curve in the first quadrant is 0.5 square unit. Similarly, the area below the normal probability curve in the second quadrant is 0.5 square units. That's what the note 3 and 4 speaks about. So the line x equal to mu divides normal probability curve into two equal parts with area 0.5. So it means area below the curve in first quadrant is 0.5, area below the curve in the second quadrant is 0.5. Next is total area under the normal curve is 1 square unit. So if you consider the complete area below this curve, then it will be 1 square unit. Next thing, the standard normal variate. See, in the above function f of x, x represents the normal variate. Here what we do here, we convert the normal variate into a standard form called as a standard normal variate. For that we use some substitution. So let us start from the normal distribution function now. By definition of normal distribution function, what we have? The probability density function f of x is equal to 1 by sigma root 2 pi into e to the power of minus of x minus mu whole square divided by 2 times sigma square. So I name it as equation number 1, where x represents normal variate. Now if I want to find out the probability of x between a and b, so it is given by the formula integral a to b f of x into dx. Now I substitute the value of f of x now. P of x between a and b is equal to integral a to b 1 divided by sigma root 2 pi into e to the power of minus of x minus mu whole square divided by 2 times the sigma square into dx. I name it as equation number 2. Now in order to convert normal variate into standard normal variate, I substitute this x minus mu by sigma as some variable z. So it is z is equal to x minus mu divided by sigma. And here x is varying from a to b. In particular, if x takes the value a, suppose if I substitute x is equal to a, we call this z to be as z1. So it is z1 is equal to a minus mu by sigma. Same way, in particular, if x takes the value b, it is z2 is equal to b minus mu by sigma. It means that for the normal variate x, the corresponding standard normal variate is z. For the normal variate a, corresponding standard normal variate is z1. For normal variate b, the corresponding standard normal variate is z2 here. So if I cross multiply this equation, I'll get this below equation. It is x is equal to sigma z plus mu, where sigma and mu are constants here. If I differentiate this, I get dx is equal to sigma into dz. So now you substitute all these results in the equation number 2. So equation 2 gives p of x between a and b. So we have converted x to the variable z. So it becomes like p of z between z1 and z2. P of z between z1 and z2 is equal to integral a to b. For the normal variate a, the corresponding standard normal variate is z1. So I take it as z1 to z2, 1 by sigma root 2 pi as it is, into e to the power of minus 1 by 2 as it is I have taken, into x minus mu divided by sigma whole square. X minus mu divided by sigma whole square is z square I get. So it is e to the power of minus 1 by 2 into z square into dx. Here dx is sigma into dz. Sigma into dz I get. So if I cancel out the sigma, I get p of z between z1 and z2 is equal to integral z1 to z2, 1 divided by root 2 pi into e to the power of minus z square by 2 into dz. So basically what does this signifies? This integral signifies the area below the curve f of z. If I take this 1 by root 2 pi into e to the power of minus z square by 2 as a function of z, then integral of this f of z gives area below the curve f of z. Okay. So here capital F of z is equal to 1 by root 2 pi into e to the power of minus z square by 2. I have taken the integrand as function of z, which represents standard normal function. And here z is equal to x minus mu by sigma is a standard normal variate. So whenever we want to find the probability of standard normal variate z between any two values, so this is the formula. It is integral z1 to z2, 1 by root 2 pi e to the power of minus z square by 2 into dz. Basically, this value represents area below the curve f of z from z1 to z2. I repeat again, this integral signifies, or this integral represents area below the curve f of z from z1 to z2. So we study some two results here. The first one is standard normal variate is a normal variate with mean 0 and unit standard deviation. It means in the function f of x, if you substitute mu is equal to 0 and sigma is equal to 1, you get f of z here. Okay, I'll just show it. If I substitute mu is equal to 0 and sigma is equal to 1 here, I get f of x equal to 1 by root 2 pi e to the power of minus x square by 2. So this function and this f of z function, both will be same. So that is what the note 1 speaks about. The next one is, in particular, when z1 equal to 0 and z2 is equal to z, then the standard normal function is given by. So in the equation number 3, in the equation 3, if I substitute z1 is equal to 0 and this z2 to be as some standard normal variate z, then this is represented by pi of z here. So p of 0 less than z less than some standard normal variate z is represented as pi of z. So this equation 3 becomes pi of z is equal to 0 to z 1 by root 2 pi e to the power of minus z square by 2 into dz. Okay, so that is what the note 2 speaks about. In particular, if I substitute z1 is equal to 0, we represent LHS as pi of z, where pi of z is equal to p of z between 0 and z. So it is integral 0 to z 1 by root 2 pi e to the power of minus z square by 2 into dz. So this integral gives area below the standard normal curve from 0 to z. So now we study some important results now. First one, how to find the probability of standard normal variate z between minus infinity to plus infinity. It is nothing but integral minus infinity to plus infinity 1 by root 2 pi e to the power of minus z square by 2 into dz, which gives the area below the standard normal curve. So I have written it in a graphical form. So it is integral minus infinity to plus infinity. So area below the curve will be equal to 1, because we know that the maximum probability value can be equal to 1. Next one, if I want to find the p of z between minus infinity to 0, it means area below the standard normal curve from minus infinity to 0. From minus infinity to 0 will be equal to 0 to infinity. Will be equal to area below the curve from 0 to infinity, because the graph is symmetric here. Therefore, the area in the first quadrant will be equal to area in the second quadrant, and it is 0.5. When you take a complete area, it is 1. When you take half of the area, it is 0.5. Next one, probability of z between minus z1 and plus z1. It should be z1. Probability of z between minus z1 and plus z1. So you can see the region here. We are interested in finding the area below the curve from z1 and z2. So this area I can write it as 2 times the area below the curve from 0 to z1. 2 times area below the curve from 0 to z1, because the graph is symmetric here. So I take it as 2 times z between 0 and z1, which gives area below the curve from 0 to z1. But we know that as a note 2. So what does the note 2 speaks? In particular, if z1 is equal to 0, p of z between 0 and z is given by pi of z. So I write this as 2 times pi of z1. Since we have z1 here, it is pi of z1. Suppose if we have z between 0 and z2, then it will become pi of z2. Next, note 4, p of z between minus infinity and z1. So it is area below the curve from minus infinity to plus z1. So if we want to find out this area is equal to area below the curve in the second quadrant plus area below the curve in the first quadrant from 0 to z1. So I take it as 0.5 plus p of z between 0 to z1. So 0.5 gives the area in the second quadrant, and p of z between 0 to z1 gives area below the curve from 0 to z1. So by the result of note 2, I can represent it as pi of z1. So this is nothing but integral. Pi of z1 is equal to integral 0 to z1 1 by root 2 pi e to the power of minus z square by 2 into dz. Okay. Similarly, when it comes to 5, z between z1 to infinity. So you can see the graph. This is plus z1 and up to infinity. I need to find the area from z1 to infinity below the curve. For that, what I do? In the complete area of the first quadrant, I subtract area below the curve from 0 to z1. So I consider p of z from 0 to infinity. 0 to infinity means complete area minus area below the curve from 0 to z1. From 0 to z1. If I subtract this area, I'll be getting this area. So this is like 0.5 minus pi of z1. 0.5 minus pi of z1. Next, sixth note, z between z1 and z2. So z1 is positive and z2 is positive. So this is the region we are interested in finding. So how to find out this? First, I find the area below the curve from 0 to z2, and then I subtract area below the curve from 0 to z1. So it is z between 0 to z2 minus z between 0 to z1. So this can be represented of pi of Z2. This can be represented as pi of Z1. Next, the last note, Z between minus Z1 and plus Z2. So here we can see the graph here. This is a minus Z1 coordinate. This is plus Z2 coordinate. We are interested in finding the area below the curve from minus Z1 to plus Z2. So if I want to find out this area, I can split this into two halves or two regions. It is minus Z1 to 0 and 0 to Z2. It is P of Z between minus Z1 to 0 plus P of Z between 0 to Z2. From minus Z1 to 0, I can write it as 0 to Z1 because the graph is symmetric. Since the graph is symmetric, this minus Z1 to 0 can be written as 0 to Z1. So minus Z1 to 0 area is nothing but 0 to Z1. You can just see the cursor here. So we will have somewhere Z1 here. Okay. So this can be written as P of Z between 0 to Z1 plus P of Z between 0 to Z2. This can be written as pi of Z1 plus pi of Z2. So whenever we're solving problem, we just use these 7 important results to find the probability of standard normal variate Z between any two given values. Moving to the problem. The marks of 1000 students in an examination follows normal distribution with mean 70 and standard deviation 5. Find the number of students whose marks will be less than 65, more than 75, between 65 and 75. Given pi of 1 is equal to 0.3413. Here the event is concerned about the marks scored by the students, and also given that mean is 70, it is mu is equal to 70 and standard deviation sigma is equal to 5. So we assign the standard normal variate now. First, let x be the continuous normal variate. This x represents the normal variate which gives the marks scored by the students, and also given mean value mu is equal to 70, standard deviation sigma is equal to 5. Now we have to convert the normal variate into standard normal variate. So the standard normal variate is given by z is equal to x minus mu by sigma. So I substitute the value of mu on sigma. It is z is equal to x minus 70 by 5. Now for x is equal to 65, we find out the corresponding standard normal variate value. So if I substitute x is equal to 65 in this relation, I get a value of z. That is, for x is equal to 65, corresponding standard normal variate is z equal to 65 minus 70 by 5. I get z is equal to minus 1. Similarly, for x is equal to 75, corresponding standard normal variate is z equal to 75 minus 75 by 75 minus 70 by 5. So which implies z is equal to 1. It means that for normal variate 65, standard normal variate is minus 1. For normal variate 75, standard normal variate is 1. Now I move to the first case of the problem. Find the number of students whose marks will be less than 65. So first, what we do here, we find out the probability that one single student score less than 65. So this probability that a student score less than 65 is given by P of x less than 65. Here x represents the marks scored by students, and P gives the probability that a student score marks less than 65. So it is P x less than 65 is equal to P of z less than minus 1. Because for x equal to 65, corresponding standard normal variate is minus 1. So x less than 65 gives z less than minus 1. So if I plot a graph for this, P of z less than minus 1 means area below the standard probability curve from minus infinity to minus 1. So here you can see the graph from minus infinity up to minus 1. The shaded region is the region of interest now. So how to find out this area? So we take the complete area in the second quadrant. This is the first quadrant and second quadrant. We take the area below the standard normal curve in the second quadrant minus area below the curve from 0 to minus 1. So in the first quadrant, in the second quadrant, the area is 0.5 minus pi of 1. Pi of 1 means area between z is equal to 0 to z is equal to minus 1. So this is pi of 1. So here we can see pi of 1 is given as 0.3413. This 0.5 minus 0.3413. So we get P of x less than 65 is equal to 0.1587. So the number of students scored less than 65 marks out of 10,000 is, the probability should be multiplied with 1000. So we get 159 students. And second case, probability that a student score more than 75 marks. So first we find out the probability for one single student. Later we multiply that with 1000. So it is P of X greater than 75 can be written as P of Z greater than 1, because for 75 corresponding standard normal variate is 1. So P of Z greater than 1 means area below the curve from Z is equal to 1 to infinity. So here you can see the graph. Z is equal to 1 is this ordinate up to infinity. This shaded part is my region of interest. So how to find this area? We take the area in the first quadrant below the curve minus area below the curve from Z equal to 0 to Z is equal to 1. So area in the first quadrant is 0.5 minus pi of 1. Pi of 1 means area below the curve from Z equal to 0 to Z is equal to 1. So this is nothing but P of 0 less than Z less than 1. I repeat again, pi of 1 can be written as P of 0 less than Z less than 1. So in the given data, pi of 1 is 0.3413. So I get P of Z greater than 1 equal to 0.1587. So if I want to find out the total number of students out of 10,000, I multiply 10,000 with the probability value. I get 159 students. Now I move to the third case. So the third case is about number of students whose marks will be between 65 and 75. So I find out the probability for each student first. Now the probability that the students score the marks between 65 and 75. So it is given by P of X between 65 and 75, because X represents marks of student. So this X is a normal variate. We convert this to the standard normal variate now. So it is P of Z between -1 and +1. This is nothing but area below the standard normal probability curve from Z equal to -1 to Z is equal to +1. So this is the ordinate Z is equal to -1 and this is the ordinate Z is equal to +1. This shaded region is region of interest. So since we know that the graph is symmetric about the line X is equal to mu, this complete area can be written as area in the 2 times the area in the first quadrant. So if I consider Z is equal to 0 to Z is equal to 1, area below the curve from Z is equal to 0 to Z is equal to 1, and if I multiply that by 2, that gives this complete shaded area. Okay, so I can write this as 2 times probability of Z between 0 to 1. So P of Z between 0 to 1 means pi of 1. Suppose if we have P of Z between 0 to 2, we get pi of 2 and so on. Okay, so it is pi of 1. That can be written as 2 times 0.3413. I get 0.6826. So the number of students score marks between 65 and 75 out of 1000 students equal to 1000 multiplied by the probability. I get 683 students.